Often the last question in an AEA paper is like some really complicated integration question. So it's nice and fresh to see that we've got a recurrence relation, including periodic sequences. Okay, we've got this recurrence relation for natural numbers n, and we're told that one of the terms in the sequence is a, and the sequence is periodic. In part A, we're asked to determine an equation for q in terms of p and a such that the sequence is constant, so of period order 1. So that means all the terms are going to equal a. And therefore, because I know that, well, the first term, let the first term be a, I guess, but it doesn't really matter. I can just say that a must equal p plus q over a. And we're trying to get q as a subject, so I can times through by a squared equals pa plus q, and therefore q is going to be a squared minus pa, or I'll just write it as ap. So if that is true, then we will necessarily get such a sequence. Part B then steps things up in asking to determine the value of p that's necessary for the sequence to be of period or order 2. That means every other term is going to be the same. And so let's first of all work out the recurrence relation. We've got an plus 1 equal to p plus q over an. And that means that an plus 2, the next one, is going to be p plus q over an plus 1. But now I can substitute in for an plus 1 and get it in terms of an, and then I can set them equal. Before I do that, it makes sense to put them over a common denominator, so that'll be a p an plus 1. It's going to look like that. Okay, and then I can actually do the same over here. So actually I'll get p an plus q over an. So what that means is that now I'll have an plus q over an plus q. It just makes it easier to manipulate the algebra. Everything's over a common denominator. And I can times through top and bottom by an without changing it. So this will give pan plus q plus qan all over pan plus q. Could expand the bracket. I think I'll leave it like that for the moment, but this is going to be, actually going to, although that's not the answer to the question, I'm just going to put a box around this because this seems quite useful because it allows me to get from one term to not the next one, but the one after that. Now remember, we're asked to determine the value of p that's necessary for the sequence to be of period of order 2. So for order 2, we can say that an plus 2 is going to equal an. And I'm just going to call them both a to avoid using the subscript. So then just a will equal multiply through remember, we're trying to get p actually I forgot what we're even trying to do. Determine the value of p that's necessary. So multiply this out. Okay, these cancel. That's quite nice. And we've actually now got a quadratic in p, so let me maybe write it as a p squared plus qp minus a squared p equals 0. I'm going to factorize out the p. Be careful not to just cancel it out because it could equal 0. ap plus q minus a squared. So p equals 0, or p equals q minus a squared over a. Now, just be careful with this one and have a little look, because what we did in part A was to actually derive that. This is the same thing. Q is a squared minus ap over p. So actually this one here corresponds to order 1. What you have to remember is we've not technically shown that it's going to be of order 2. We've just shown when one term is equal to not the next one, but the one after that. So that would also be true for a sequence of order 1. But it's nice to see that solution, also existing. It has to. Therefore, our answer is going to be p equals 0. Part C says give an example of a sequence that satisfies the condition in B, that is p0, but is not of period or order 2. Okay, let's just remind ourselves, this is our recurrence relation. And it's going to become an plus 1 equals q over an. So let's say my first term is a, then I would put that in and I'd get q over a. I would then put that in and I'd get q over a, which would take me back to a, and so on. So this looks like it's going to be order 2, but what would I need for these two to actually be the same? A equals q over a, meaning that q would equal a squared. So I just need to give an example of that. I'm going to let a equal 3 and then q equal 9. So an plus 1 here would equal 9 over an, with a1 equal to 3, and this gives 3, 3, 3 is our answer. So as long you can use anything, you could use, as long as q is the square of a, that's what I've shown in the question, then that would give you a solid example. This has order 1. Just going to conclude that. So what this is saying is that p equals 0 doesn't guarantee a sequence of order 2, because it will depend on your u and your starting number as well. Okay, great. This takes us to the last and most epic part, to determine an equation for q in terms of p only, such that the sequence has period or order 4. Okay. Now, one thing you could start with is an plus 4 and get it in terms of an plus 3, but there's a better way, because earlier on we found a relationship between a term and then the one, not the next one, but the one after that. So we can just use that essentially. So this is an plus 2, and it's all over a common denominator. The only thing I'm going to do is slightly rearrange it so that I factorize out the an at the top. Therefore, it will become p squared plus q an plus PQ all over PAM plus Q. Okay, so what that means, I mean, this gets complicated. So like any kind of thing you can notice that's going to make your life a bit easier, such as this, is really going to help. So AN plus 4 is going to be this exact same thing again, but I just replace all the n's by n plus 2's. And now I'm going to substitute in to this and this thing here. So we've got p squared plus q multiplied by, in a big bracket, p squared plus q an plus pq and then plus pq. Oh, but that's not being times by the p squared plus q. Okay, so make sure we close that bracket. All over p times that same thing again. Okay, now straight away I can multiply through by PAN plus Q because I really don't want that on the denominator. So this is gone, and it ends up over here. We're just timesing top and bottom by this PAN plus Q. Okay, nice. And here's the thing, this is going to equal AN for a sequence of order 4. So I'm just going to set them both equal to A. Solve. And I'm also going to times through by the denominator. So solve A P plus AQ. So I've basically I've called this A and I've times both sides of the equation by this denominator. And that is then going to equal that numerator Oh, and sorry, I forgot the PA plus Q there because I've written it in purple. Okay, so we've got this equation to deal with. Now, before we move on, I just want to remind you, we actually know that P equals 0 is a solution because this was what we got for order 2. And if it's order 2, then the first and the fourth are also going to be the same. And then we had that earlier condition relating P and Q. It was all the way up here. That was for order 1. I think I missed, was that everything? Yeah, okay. So that means that we're potentially looking also to factorize, we're looking to factorize P out, but also this expression here. So AP plus Q minus A squared is a factor. Or we might have it as A squared minus Q minus AP. This was order 1, which would also satisfy the condition that we have for order 4. So let's continue to, manipulate this equation. It doesn't look very nice, does it? Okay, so I'm gonna do it bit by bit as well. So I'm gonna multiply the first square bracket. So AP times P squared plus Q times A, that makes it A squared, plus A P squared Q. Okay, that bit is sorted. Then this next bracket I'm going to multiply out completely, so it will be A squared QP plus AQ squared. That will equal P squared plus Q squared, actually, times A plus P squared plus Q times PQ plus P squared QA plus PQ squared. Okay, all right, let's expand again. Right, double bracket here. So P to the 4 plus Q squared plus 2 P squared Q. All of that's multiplied by A. That's what we're going to get. Okay, now I know, remember, that P is going to be a factor, so like any term without P in it must cancel out. In fact, that is going to cancel out with that one. Do you know what? I could factorize the P out, but I think I'm just going to say P equals 0, or, and then I'm going to write the whole thing out again, but divide through by P. Okay, let's just stress something out. All right. Can we cancel anything else out? We've got an APQ here and an APQ here, so they cancel. Now I'm going to start collecting terms up as best I can. So actually here I've got A squared. Oh no, that doesn't work. Right, I've then got A squared Q here and A squared Q here. So A squared P squared plus 2 A squared Q. Can I combine any? Yes, there's some that I can combine. P to the 3A. Okay, and we've ended up with 6 terms. Now, remember what I said about one of these like being a factor as well. If we know that must, like, if we factorize it, well, we will be able to factorize it. This must be a factor. So I think the first thing to do is get it all on one side. I think I'll get this over to here. Okay, so I'm just gonna take out a factor of, what should we go with? Let's go with the first one, AP plus Q minus A squared. Now, there are 3 terms containing a 2. So I wonder if I can factorize the 2 out. And then what am I left with? Well, I've got a Q squared on this one. So if I took a Q out as well, then that will get me my Q squared. And I've got minus 2A squared Q. That comes from this one. And I've got this one here comes from this one. So I've managed to deal with these terms. That would come together. And then I want the same thing. I don't want to do this too quickly. AP plus Q minus A squared. Right, now if I factorize out P squared, then I'll get my P cubed A from here. I need P squared Q, that will come from here. And this one here is there as well. And that will equal 0. Believe it or not, we're nearly there. This is awkward. I've said that a few times now, but okay, what we can actually now do is, look, I've got a common factor, so I can just factorize out the whole thing. I'm left with here 2Q plus P squared equals 0. So we've already dealt with P's 0. I just want to say that again. I decided to divide by it. I could have factorized it out. In the official solutions, they factorize it out. So P equals 0. Remember, that would be order 2. This one here equaling 0 gives order 1. So neither of those are actually solutions here. So for order 4, we require 2Q plus P squared equals 0. And therefore Q is going to equal minus P squared over 2. It becomes that simple. That is the condition. Oh, fair play if you got that. Like, it's you're nearing the end of the exam. You got to do all this algebraic manipulation. Yeah, it's tough. Look how many lines we've done there. So I think this is a fantastic question. It really, like, just links in certain properties to get order 1, 2, and then finally 4, which we managed to do here. Thanks for watching, and very well done.